Okay, so today we're moving on to have a look at phenols. So remembering our knowledge of our reactions from arenes and then developing those as we have a look at our phenols. Now, before we launch fully into our phenols, I just want to do a quick recap of the mechanism that we set you as a photo upload. So that was to work out what you would get if you reacted benzene with 2-chloropropane. Oops. CH, there we go. CH3. Okay, so we had lots of good answers, but there were some common mistakes as well. So it's worth just kind of running over this before we go on. So first of all, we need to worry about generation of the electrophile when we are writing out our mechanisms. So we had a haloalkane there. So we need our halogen carrier, our AlCl3. And I'm not doing well with my writing today, AlCl3 plus CH3, CHCl, CH3. Now we are going to remove the chlorine to give us AlCl, Cl4 minus, and then we're left with our electrophile. Now, when we're doing this, bear in mind the location of the Cl. So the Cl is bonded onto carbon number 2, which means that our positive charge is going to be on carbon number 2. And we can make sure we show this. So CH3, CH, put the positive charge there, and this will help you in the next step. So that's our electrophile. Draw it out with a display formula if you prefer. So next step then is our curly arrow mechanism bit. So we have our benzene ring. We need to have our electrophile, and now if we do draw it out here, it'll probably make things easier. So I'm going to draw that middle carbon first. So it's got a hydrogen attached there, and then it's got the 2CH3. So you could do those displayed or just structurally like that, if that's easier. And then that positive charge, rather than just sticking it anywhere, let's put it in the right place. Because now, hopefully looking at that, you can see that it's very clear as to where we need our curly arrow to go. So it starts on the ring and it goes to the carbon with a positive charge. So then we can draw out our intermediate, remembering that we open up the ring towards the carbon that we've decided to bond our electrophile to, show the original hydrogen that was there as well. So this now has CH3, H, squeeze on that other CH3 there. And then we need, I forgot my positive charge in the middle, don't forget that. Then we need to lose our hydrogen. So curly arrow from midway along the bond where the bonding electrons are, back into the ring there. And then that gives us our final product. So the reformed ring, and then we have C, CH3, H, CH3. So it's critical that we make sure the positive charge is on the correct carbon in order that we end up bonding onto the correct carbon and don't end up with some kind of strange structure with the wrong number of bonds around carbon. Don't forget as well to put down that H+. That's a bit I always forget there. And then finally, we need to regenerate the catalyst. Okay, so we had our AlCl4 minus produced when we did the production of our electrophile in the first place. We've got our H plus that we've kicked off, put those together, and we get our AlCl3 catalyst, regenerated, and we get HCl as our other product. So that's what the one that we were looking at last time should have been like. Okay, so now having a look at phenols. So the PowerPoint today is going to guide you through the usual steps. So having a look at physical properties and then having a look at the reactions. First of all, make sure we have a think about naming. So a phenol must contain this unit here. So a benzene ring with an OH attached. In terms of naming these, you need to name them in a similar way to we did with our arenes, in that any substituents will be added on. So like if we've got a methyl group, a chloro group, and so on. A few people were asking me questions last week about when we use the phenyl name, and the phenyl name is used when we've got C6H5 as a group. So a good way of working out whether you need to use that is to look at your structure and then have a look at what's attached to it, and then see if what's attached to it, if the benzene ring was replaced by an H, is that a molecule with a functional group? And if it is, name that first, and the benzene ring becomes a branch. So if we were to replace our benzene ring here with a hydrogen, we'd have methanol over there. So this becomes phenyl methanol. If we are comparing where we could have all the same atoms and we've got a CH3 there, then what we've got now is a methyl branch. Okay, so this one is going to be methyl phenol, and then we could add numbers in according to the position on the benzene ring there. Okay, so if in doubt, look at the molecule, cover up the benzene ring. Is there a functional group in what you've got added onto the end that would enable us to name that as a molecule if we put an H where my hand is? If yes, name it and add phenyl on. Otherwise, have a look, and if the branch is just a carbon-containing chain, just carbons and hydrogens, name that as the branch and the rest of the molecule as the actual molecule. Okay, so that's how to name these things. It's a little bit more practice for you to start off with in the PowerPoint. Physical properties run through on the PowerPoint. We can have hydrogen bonding when we have phenol, because we've got an oxygen attached to a hydrogen there. Okay, whoops, there we go. So we've got the delta plus, delta minus, lone pair, so you can draw out your hydrogen bonding. Okay, these aren't massively soluble because the hydrogen bonding part of the molecule is a small proportion of the overall molecule. And so this section here isn't going to interact with water, only this bit. So they're kind of partially soluble, a little bit soluble, but more so than other things of similar molecular weights that couldn't undergo hydrogen bonding. Phenols are interesting in that, so you look at them and think, okay, it's like an alcohol, an OH and an alcohol, but they don't behave that way. So we talked, when we were talking about the directing effects before, about how the lone pair on the oxygen can be delocalized into the ring. And that enables our phenoxide ion to be more stable than you might otherwise expect. And so compared with alcohols, this equilibrium position lies reasonably far to the right-hand side, just compared with alcohols. If we were comparing with carboxylic acids, relatively speaking, it's over to the left-hand side. But it does mean that a phenol is weakly acidic, because the lone pair of electrons here can be passed, delocalized into the ring, giving you additional stability. And the more stable the anion that is formed through the loss of the hydrogen is, the further to the right-hand side the equilibrium position would lie. And so we do lose some H plus ions, and so we have acidic character here. This also means, because it can behave as an acid, that it dissolves quite well in alkalis, because when we have our phenol, we can react it with sodium hydroxide and we can form sodium phenoxide. And once we've got sodium phenoxide, then we've got an ionic compound. Ionic compounds will dissolve because you've got the electrostatic attractions between the ions and the polar water molecules. And those electrostatic attractions are going to be much stronger than the simple hydrogen bonding that we would have just looking at the organic molecules. So once we've converted it into an ionic substance, it's going to be much more soluble. Now, in terms of the reactivity of phenols, we need to again think about the delocalization into the ring. So if we have a look at our phenol structure. So remember when we had a look at benzene and we looked at the fact that the p orbitals perpendicular to the plane of the molecule can overlap. So if I then add on the OH, so we've got the lone pairs on the oxygens, which means that we've also got electrons available in the p orbital here. And so we can get greater delocalization into the ring. So that was the above one. Let me draw the below one. Than we had with our arene. And because of the delocalization of the lone pair in the p orbital and the oxygen into the ring, we have an increased electron density. So if we've got an increased electron density here, and we have, for example, our bromine molecule approaching. So remember with the arenes, you couldn't have a direct reaction between benzene and a bromine molecule because the electron density wasn't sufficiently high in order to polarize this like you would expect if it was an alkene. Now we've got an enhanced electron density. So as our bromine molecule approaches the ring, so the high area of electron density, electrons are going to be repelled from this end, leaving that delta positive, and shoved over this end, leaving that delta negative. And then that is going to allow our ring electrons to be sufficiently strongly attracted to the delta positive area to have a reaction without a catalyst. Okay, so with benzene, we need to have our aluminium chloride halogen carrier in order to generate the electrophile. The electrophile then has a full positive charge, allowing the attraction between the ring of electrons and the positive charge. But here, with our increased ring electron density, we can get away with just having a delta positive charge, so a lower positive charge here, but we still have a strong enough attraction in order to cause the reaction. So the overall mechanism for this one would then look like this. So I'll draw this one out for you, and then I will leave you to have a look through the PowerPoint and write down the various notes and sort out the other reactions. So we can have our dipole, ring comes out, electrons from the ring come out and attack the bromine, bond breaks, and the electrons go out to the bromine like that. Then our intermediate looks very similar to when we have our benzene reaction. So we've now got a bromine attached there, hydrogen's there, and we kicked off our Br minus. And then we've got our curly arrow with our electrons from the carbon-hydrogen bond coming back in and forming the ring. And this will be our product. And we've got H+. So overall, we have produced bromide ions and hydrogen ions, so we get HBr as our second product there.